Mathematical induction is a proof technique used to prove statements which assert that the propositional function p of n is true for all positive integers n. So a good way to visualize this is if we imagine an infinite ladder, and we know two things. One, we can reach the first rung, and two, if we can reach a particular rung, we can reach the next rung. So we can write this out. If this is the first rung, p of 1 implies p of 2, meaning we can reach the second rung. And we can just apply number 2 again and say p of 2 implies p of 3. And using induction, we find that for an arbitrary integer k, we can find it implies p of k plus 1. So induction is good because it can be used to prove a conjecture, but it's also bad because it can't be used to find new theorems because it doesn't offer any mathematical insight as to why a theorem is true.
Okay, now if we were to prove a statement through mathematical induction, there are 3 steps we have to follow. If we take a look at this case, the summation from I equals 1 to n of 2I minus 1 equals n squared, we'd start with our base step. Now, the base step is where we verify the discrete case through by hand, usually of 1 or 0, but it can be any term. So the base case in this example, we would do p of 1. So here, when we plug in 1 to I, we get 2 times 1 minus 1 equals 1. 1 squared is 1. So we prove that the base case is 1. The next step would be your inductive step. And this is where you assume an arbitrary k is true and use that assumption to prove that p of k plus 1 is true. So, in this case, we have p of k, which is equal to k squared, from our assumption. And then we would go about proving p of k plus 1. So, p of k plus 1 is the sum of all odd integers. So it would be 1 plus 3 plus 5, all the way to our term. The previous term would be k, which would be expressed as an odd integer is 2k minus 1, plus our term right here, 2k plus 1. Now, if we assume that the summation of all terms before it is p of k, and we prove that p of k is k squared, we can just use that sum plus our last term to get p of k plus 1. So it's equal to k squared from here, plus our last term, 2k plus 1. P of k plus 1, when we simplify this, is k squared plus 2k plus 1, which is equal to k plus 1 squared. We can see that this holds true because if we plug in k plus 1 into here, into n, it would just be k plus 1 squared. Thus, we go through each step, the base step, proving it for true for one discrete case, the inductive step for p of k, and then we conclude that p of n is true for all n because we proved k and k plus 1.
So another way to look at the mathematical induction is this logical expression here. P1 is true, and for every k, such that pk implies pk plus 1 is true, and we can conclude that for every n, Pn is true. And here's one example. want to prove that n is less than 2 to the n. So we'll start with the basis step. We'll use P1 as our base case here, and see that 1 is less than 2 to the power of 1, so P1 is true. Now that we have verified the basis step, we'll proceed to the inductive step. We assume that pk is true. And now we need to show that pk plus 1 is also true. So pk is true, so k is less than 2 to the k. And when we add 1 to both sides, we get 2 to the k plus 1. And we know that this is less than or equals to 2 to the k plus 2 to the k. From here we can say that k plus 1 is less than 2 times 2 to the k, which is 2 to the power of k plus 1. So let's just show that pk plus 1 is true. Since pk implies pk plus 1, now we can conclude that pn is true for all positive integers n.
So some common errors with mathematical induction. One is the horse problem. So say we're trying to prove that all horses are the same color. So we'll start with the expression p of n, which says p of n, which says that for any set of n horses, they're the same color. So let's try to prove this for all n. So we'll start with p of 1, which is true because any set of one horse, all the horses in the set are the same color. And now we'll assume p of k, which means that set of k horses are the same color. So then we'll use this to prove k plus 1. So now we have some set of horses, 1, 2, all the way to k plus 1. Well, we have this set 1, 2 to k, which is a set of k. Because we know p of k is true. We have this other set, 2, 3 to k plus 1, which is a set also of size k. And since these sets intersect, all the horses must be the same color. So we can conclude that for all n, p of n, or that every horse is the same color. But the problem here is that p of 1 does not imply p of 2. Because if you have two sets, or if you have a set of two horses, then the set 1 of just one horse and the other set of just one horse don't intersect. So p of 1 does not imply p of 2. So in order to use induction, your implication must be mathematically rigorous.
Another error is not proving the base case. So say we're trying to prove P of n, which says n equals n minus 1. So we'll assume P of k is true. Say k equals k minus 1. We'll add 1 to both sides. We'll say k plus 1 equals k plus 1 minus 1. And we've proved P of k plus 1. So we can falsely conclude that P of n is true for all integers. But what we failed to do is prove a base case. So if we plug in 1, we get 1 equals 0, which is obviously not true. So our induction is invalid.